Next, we're going to talk about multiple source localization. This is just an extension of this idea. So instead of one source now, we have several sources. So instead of receiving just a single weighted Green's function, we're going to receive a weighted sum of several of these, each with their own source, each with their own complex amplitude alpha s, plus some noise term. We want to simultaneously estimate all these source locations. Okay, so this is what we would do if we could. We would do a global search, basically. So we would do the same kind of approach that we did before. We'd do least squares estimate, and we'd minimize this over all source locations R of S and all complex amplitudes beta of S. Unfortunately, this is a combinatorically hard problem to solve over all the different source locations. But it is essentially a sparse approximation problem. It's very common to what we have encountered in other types of compressed sensing approaches. So the main idea is to use something similar, like a greedy approach, like orthogonal matching pursuit, with a parameterized dictionary. Okay, so here's what this looks like, basically. If you have some estimates for R1 and R2, then you can estimate R3 by itself. So you basically subtract out beta 1g R1 and beta 2g R2 from your data vector y, and then you estimate only the third source location using the standard approach. So this residual must be orthogonal to all of the Green's vectors. So we can substitute just this projection matrix applied to y minus beta s g r of s when we're estimating the s source location. And this is equivalent to just maximizing this inner product that's basically weighted through this projection matrix P of S divided by this G of R squared to normalize everything. So this P of S is just constructed so that it will null out any contribution that comes from any of the known Green's functions, essentially. So alternatively, we can apply this projection matrix to both the data vector and the Green's vector if we want to jointly estimate both the source amplitudes that are corresponding to the known source locations and the new source location. So we can construct this projection matrix from the concatenated Green's functions. So if we just place all of these Green's functions together and apply this pseudo-inverse from G to itself, we can construct this projection matrix. Or alternatively, we can construct this projection matrix from the correlation matrices eigenvalue decomposition. So essentially, if you just sum over all of the source locations, this outer product of this Green's functions, except for the source that you're currently trying to estimate, and you find some eigenvalue decomposition, then you construct this P of S just as I minus this V and R Hermitian, where this V and R is basically a truncated eigenvalue decomposition to be rank NR, essentially. NR is the number of source locations in this case, and I'm writing it this way so that we can put a twist on this later. So here's the basic algorithm for Romulo. So we're repeating this inner loop until some stopping criterion. And so what does this inner loop do? It's looping over all the source locations. And at each iteration, it's estimating a correlation matrix that has all of the Green's vectors except the one that we're currently estimating. Then we take this correlation matrix Q of S and we take its eigenvalue decomposition. We take the NR largest eigenvalues, eigenvectors corresponding to the largest eigenvalues. And we map this into this projection matrix, and then we perform least squares estimation to estimate our new source estimate, and we iterate through this repeatedly. So to show you what this looks like, this is a standard ambiguity function with 10 sources. So the source locations are shown with these red circles. So by maximizing it, we find the first element here, and we subtract off this Green's vector from the data vector. And now the next maximum is going to be somewhere over here. If we run this for the first 5 times, we come up with the first 5 source estimates. And then after we run this through 100 times, we find all of the source estimates And each one of these source estimates has been revisited 10 times. And this is the last one that we'll estimate here. So at every iteration, we basically forget one of these source locations and re-estimate its location. And also we're going to talk about a robust variation. So instead of estimating each location by presuming that we know the other two exactly, we're going to introduce some uncertainty into the locations for R1 and R2. So instead of computing this correlation matrix in this way, we're going to presume that we only know these locations to within some certain ellipse. So the idea is that we want to minimize the influence of any Green's vector that lies within this ellipse on the data vector, basically. So in order to make this more robust, we're now constructing our correlation matrix as the sum of these areas, which are ellipses. So we're basically integrating over this GR Hermitian in order to make a more robust correlation matrix. So to compare these two, this is the kind of a standard approach. This is using point nulling, and it acts like a notch filter. And in this case, the correlation matrix is low rank, and its projection rank is just equal to the number of sources that you have, which is just S naught in general. In this new proposed approach, we're proposing using a robust nulling approach, which is acting like a band reject filter. And so it's approximately low rank, but not quite. And we can truncate this matrix using a rank of about 1.5 times the number of sources to give us good results. So this is acting a lot like SVD thresholding or PCA projection. It has a lot of parallels with DPSS approaches. And it gives near optimal attenuation in terms of the least squares approach in the region of interest without attenuating the other areas too much. So this is an example of what this type of filter looks like. So if you want to construct a rank 5 matrix that nulls out this area here, it has a smooth transition region around it, which nulls out other areas that are nearby as well. And for this reason, you cannot localize two sources that are very close to each other, because if you estimate one source, it kills off the energy of the other source. This is what a rank 20 matrix looks like for nulling out several of these ellipses simultaneously. So again, this is a filter just ranging from 0 to 1. 1 means you pass all the energy, and 0 means you stop all the energy, essentially. And these are all transition regions in between here. So in the coherent case, again, as before, if we have some source transmitting with known frequencies and known amplitudes, but some unknown attenuation beta, then we can stack these vertically to give these concatenated results. And the projection matrix now is constructed across all frequencies. So there's this joint large SVD that's being computed, which can be difficult if it's being computed every iteration. We use an approach to speed this up using a randomized SVD that was proposed by Trop, and it runs reasonably fast. And it's, again, as before, has the same formulation as the single frequency case, so we're able to compute this result rather quickly. So for the incoherent case, suppose we have amplitudes that are unknown, then we just construct the standard projection matrix on a per frequency basis, so we don't need any large SVD. And now we're just summing the per frequency ambiguity functions together to give us our results using this projection matrix. And as before, also, this extends very naturally to compressive measurements. So simply by substituting phi k, yk for the standard yk, and likewise for the Green's function, then we're able to achieve this type of compressive approach that works well. And can speed up and yield a computational advantage of n over m times fewer PDEs that we have to solve. So this is what this looks like. This is comparing the robust approach to the point nulling approach. So you can see that for 2 measurements, and both 2 and 4 measurements, that the robust approach works slightly better than the standard point approach. And this is using the same distance metric as before as well. This is a comparison between this greedy scheme that we're proposing and the globally optimal scheme. So as I mentioned in the beginning of this part, ideally we'd like to be able to solve both source locations jointly, but this is combinatorically hard. It's barely feasible with in the two-source case, and so we can show results for this, and we can give an idea of how close it comes. So although the greedy approach does much worse than the global approach, it's important to note that in many cases the global approach just isn't possible, and we have to instead use something that is suboptimal because it's the only thing we can do. And this shows the region of uncertainty for localizing two sources that are close to one another. So if you have one source that is localized within this green ellipse here, the question is, where can you localize a second source? How far away do they have to be from each other? So this black region up near the top of the plot is showing that if you have two sources that a second source that is within this region, you cannot find both of these sources to within their target ellipses. If you essentially need the second source to be far enough away from the first source to where they can be disambiguated.